A fast-moving object the size of Manhattan is hurtling towards our solar system.
What if an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond?
Across the dark expanse beyond Jupiter's orbit, an object from another star has become the center of one of the strangest rumors in modern astronomy. Videos, headlines, and social media posts have exploded with the claim that the interstellar visitor 3I Atlas has just reduced its speed by 300%. Is that even possible, though? And what really is happening? Well, this is one galactic journey you can't miss.
We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system.
You will be shocked. The third interstellar visitor. On the first day of July 2025, the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, operating from its Southern Survey Station in Chile, detected a faint, fast-moving point of light crossing the starfield of Sagittarius. Automated processing flagged it as an unusual near-Sun object, but subsequent orbital calculations revealed something extraordinary. Its trajectory was not elliptical, nor even parabolic, but hyperbolic. This means that it was unbound to the Sun, moving too quickly to have originated within the solar system. Within days, the International Astronomical Union's Minor Planets Center confirmed its status as an interstellar body and named it 3I Atlas. This placed it after one I Oumuamua, detected in 2017, and two I Borisov, found in 2019. At the time of its discovery, the comet's apparent magnitude was approximately plus 18. Faint enough to require long exposure imaging, yet bright enough to allow rapid astrometric tracking. Early calculations by the Jet Propulsion Laboratory's Horizon system indicated that it was inbound toward the inner solar system on a steep retrograde path inclined about 54 degrees relative to the ecliptic. Its hyperbolic excess velocity, meaning the speed it would retain even after escaping the Sun's gravity, was measured near 26 kilometers per second. When combined with solar acceleration, the total inbound speed reached close to 60 kilometers per second, or about 130,000 miles per hour, relative to the Sun. This makes it one of the fastest natural bodies ever recorded in our planetary region. But wait, the unusual part doesn't end here. There's a lot more to this interstellar visitor of ours. 3I Atlas is expected to reach perihelion, its closest point to the Sun, sometime in December 2025, at a distance of about 0.8 astronomical units, or roughly 120 million kilometers. Its trajectory projected that its nearest distance to Earth would be around 1.8 astronomical units, almost twice the span between the Earth and the Sun, meaning it posed no risk of impact or significant gravitational perturbation. The confirmation of 3I Atlas's interstellar nature ignited a rapid observational campaign from the world's leading observatories. The Hubble Space Telescope, despite its aging optics, captured ultraviolet spectra of the object within weeks of its detection, revealing strong emission from hydroxyl radicals, a clear signature of water vapor breaking apart under solar ultraviolet radiation. Ground-based instruments such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii confirmed the presence of carbon monoxide and carbon dioxide in the escaping gas, identifying it as a volatile rich body similar in composition to long-period comets native to the outer Oort cloud. The James Webb Space Telescope followed up with infrared spectroscopy in August 2025, obtaining unprecedented detail of the molecule-rich coma. Webb's data showed emission bands of water ice, carbon monoxide, carbon dioxide, and organic compounds, all radiating from an active surface being heated as it neared the Sun. These observations indicated that 3I Atlas was far from inert. Rather than being a passive rock like Oumuamua, it was an energetic, classic comet whose activity rivaled or exceeded that of typical solar system comets of comparable size. NASA's Planetary Science Division reported that the object was releasing water vapor at a rate comparable to a terrestrial fire hose, expelling an estimated 500 kilograms of water per second at its most active phases. For a nucleus estimated to be only a few kilometers across, that rate was among the highest ever measured. Spectroscopic analysis provided further clues to its origin. The ratio of carbon monoxide to carbon dioxide was measured at roughly 1.2 to 1, higher than the typical solar system average, suggesting formation in an extremely cold region, perhaps the outer disk of a distant stellar nursery, beyond 30 astronomical units from its host star. The relative abundances of deuterium in its water molecules also differed from known solar system values. All of this means that 3I Atlas was not merely passing through. It carried within it a chemical record of a planetary system light years away. Determining the comet's physical scale proved more difficult. Its brightness fluctuated with outgassing, and the coma's opacity made direct imaging of the solid nucleus impossible. By comparing reflected sunlight and dust production rates, researchers derived a probable nucleus diameter ranging from 0.3 kilometers at minimum to 5.6 kilometers at maximum. The uncertainty stemmed largely from the uncertain albedo, or how reflective the surface was. If the nucleus was dark and carbon-rich, it would need to be larger to produce the observed brightness. If it was icy and reflective, it could be smaller. A separate mass estimate, derived from gas flow models and non-gravitational acceleration data, proposed a total mass on the order of 3.3 billion metric tons. Though large, that figure remains tentative and depends on assumptions about density and internal porosity, which are not yet directly measurable. The comet's trajectory continued to refine as additional astrometric data came in. By late August 2025, NASA's Jet Propulsion Laboratory had reduced uncertainties in its orbital elements by a factor of 10. The refined orbit confirmed a hyperbolic eccentricity of about 1.17. This means that its path was open and it would never return. NASA continued to monitor it via multiple instruments. The Hubble Space Telescope provided ultraviolet spectra of photo-dissociated hydrogen and oxygen, allowing the determination of water production rates. The James Webb Space Telescope continued collecting near and mid-infrared data to trace organic molecules and dust emission. Meanwhile, radar facilities like the Deep Space Network's Goldstone antenna attempted, though with limited success, to detect radar echoes that could reveal size and rotation. The Lowell Observatory and Pan-STARRS contributed photometric light curves that hinted at a slow rotational period, perhaps 12 to 15 hours, but these results remain preliminary. The international interest extended beyond NASA. The European Space Agency's Comet Interceptor team, originally scheduled to launch in 2029 to target a future long-period comet, examined whether a theoretical trajectory adjustment could ever allow a spacecraft to intercept an interstellar object like 3I Atlas. They concluded that with current propulsion technology, interception at the required velocity over 50 kilometers per second was infeasible without many years of lead time. Nonetheless, the appearance of a third interstellar body renewed discussion about developing rapid response missions capable of chasing future arrivals. The scientific importance of 3I Atlas lies in its chemistry as much as its motion. Each interstellar object provides a direct sample of matter from another stellar system. Laboratory analysis of its light offers clues to planetary formation processes beyond the Sun's reach. Spectra showing elevated carbon monoxide fractions imply that the comet's ices formed under lower temperatures than those typical in the solar system nebula. likely below 25 Kelvin. This suggests that its home system may have been a colder, perhaps dimmer star, or a region of a protoplanetary disk far beyond any giant planet equivalent. The detection of complex hydrocarbons within its coma supports the idea that organic chemistry is widespread in interstellar environments, potentially seeding young planetary systems with prebiotic compounds. When it rounds the Sun and begins its outbound journey in early 2026, it will gradually fade from view, accelerating toward the outer solar system and eventually beyond the heliopause. At that point, it will once again become a wanderer between stars, carrying traces of the Sun's dust on its surface. Scientists expect to track it until at least mid-2026, after which it will be too faint for even the largest telescopes. But wait, there's more. Orbital behavior and anomaly claims. The motion of 3I Atlas conforms to Newtonian and Keplerian dynamics within standard observational uncertainty, but there have been some non-gravitational accelerations. The term non-gravitational acceleration refers to minute thrusts generated by the uneven release of gas and dust as the comet's ices sublimate under solar heating. This has been the case with 3I Atlas. The deviation is comparable to those measured for known solar system comets, such as 67P Churyumov-Gerasimenko during the Rosetta mission in 2015. In physical terms, the velocity change is only a few millimeters per second per day, far too small to produce any visible deviation to the naked eye. Regarding the claims that 3I Atlas had reduced its speed by 300%, the notion is utterly nonsensical. A 100% reduction in speed would imply a complete stop, an impossibility for a body traveling tens of kilometers per second through near-vacuum space without an external braking mechanism. Moreover, any true deceleration of even 1% would produce an observable shift in the object's predicted position, measurable by multiple observatories within days. None were reported. Instead, the only genuine variations detected were subtle perturbations consistent with outgassing jets, or small transient emissions of gas and dust acting as weak thrusters. As sunlight heats the nucleus, volatile ices, particularly water, carbon dioxide and carbon monoxide, sublimate, creating localized jets that exert a reaction force on the nucleus. For a typical comet of a few kilometers in diameter, each active jet can produce a force equivalent to only a few newtons. When combined across the surface, these can yield cumulative accelerations measurable over weeks, but still negligible compared to the Sun's gravitational pull, which exerts a strong inward acceleration. Non-gravitational effects are roughly 10 million times weaker than the dominant solar force acting on the comet. ESA's Orbital Mechanics Group in Darmstadt, Germany, published its own model of 3I Atlas's motion on September 29, 2025, using independent astrometric data from the European Southern Observatory's Very Large Telescope and the Pan-STARRS network in Hawaii. Their analysis confirmed that 3I Atlas remains on an unbound trajectory that will carry it past the Sun. Solar radiation pressure, a small outward push exerted by sunlight, also contributes to minor variations in the orbit of dust and gas around the comet, but has an almost negligible effect on the nucleus. Nonetheless, such pressure can subtly shape the morphology of the cormorant tail, which might visually appear to bend or change orientation when viewed from Earth. Further insight into the dynamics of 3I Atlas comes from photometric monitoring of its rotation and jet activity. The Lowell Observatory's photometric campaign in September 2025 detected periodic brightness variations with a period near 14 hours, consistent with a rotating nucleus whose illuminated areas alternately face the Sun. These rotational effects cause momentary asymmetries in gas release, producing small transient velocity changes typically measured in millimeters per second. In extreme cases, such outgassing torques can alter a comet's spin rate by a few percent over weeks, as was observed in Comet 9P Tempel 1 following the Deep Impact mission in 2005. However, no comparable structural changes have been observed in 3I Atlas to date. The notion of interstellar objects exhibiting anomalous accelerations originates largely from the case of 1I Oumuamua, which displayed a measurable non-gravitational acceleration that could not be fully explained by standard outgassing models. In contrast, 3I Atlas shows vigorous, continuous outgassing visible across multiple wavelengths, providing a clear physical mechanism for any slight accelerations detected. Astronomers at NASA's Goddard Space Flight Center analyzed mid-infrared observations from the James Webb Space Telescope between August and September 2025, and concluded that the observed acceleration vector closely aligns with the Sun-Comet line, matching expectations for thermally driven outflow. During perihelion passage in December 2025, 3I Atlas is expected to accelerate slightly as it descends deeper into the Sun's gravitational potential, reaching maximum velocity near 66 km per second. As it recedes, it will naturally decelerate, eventually stabilizing at its hyperbolic excess speed of roughly 26 km per second as it escapes the heliosphere. But wait, there's more. Avi Loeb's hypotheses and interpretations. Harvard astrophysicist Avi Loeb, currently director of the Galileo Project and professor of science at Harvard University, became widely known in 2018 when he proposed that the interstellar object 1I Oumuamua might have been artificial in origin. His argument, published in the astrophysical journal Letters, centered on the fact that Oumuamua showed no detectable coma, yet exhibited a measurable non-gravitational acceleration. Loeb suggested that such behavior could be consistent with sunlight-driven propulsion acting on an extremely thin, reflective structure, such as a light sail. Following the discovery of 3I Atlas, Loeb publicly stated that the object presented another opportunity to test whether some interstellar bodies might be technological relics. He has drawn parallels between 3I Atlas and earlier anomalies associated with Oumuamua and the 2019 interstellar comet 2E Borisov. Loeb's interpretation of 3I Atlas begins with photometric data suggesting the comet's reflectivity may be higher than typical for long-period comets. Loeb argued that such brightness could imply an unusually smooth or metallic surface, although planetary scientists at NASA's Goddard Space Flight Center cautioned that apparent reflectivity can be overestimated when a comet's dust coma is dense and strongly forward-scattering. Still, Loeb pointed to this as an interesting deviation worth investigating, suggesting that if the object were composed of exotic alloys or unusually reflective ices, it might hint at artificial origins. Another focal point of Loeb's reasoning concerns the symmetry of 3I Atlas's outgassing. Most comets display asymmetric jets, with localized plumes emerging from discrete active regions on the nucleus. However, early imaging from the Hubble Space Telescope in August 2025 revealed a coma that appeared roughly spherical, with no dominant jet features. Loeb interpreted this symmetry as potentially inconsistent with standard outgassing dynamics, speculating that it could indicate a uniform surface material or even an engineered mechanism that distributes gas evenly. He suggested that if outflow were artificially regulated or isotropic due to a manufactured design, this might explain why non-gravitational accelerations remained small and steady, unlike the fluctuating thrust patterns typical of natural comets. In interviews during August 2025, Loeb also referenced the relatively small range of measured non-gravitational acceleration values for 3I Atlas, similar to those observed for active comets but significantly smaller than the acceleration detected in Oumuamua. He proposed that this steadiness might indicate either an inactive or controlled propulsion process rather than chaotic sublimation. In his view, if an extraterrestrial civilization had developed small interstellar probes powered by sunlight or by controlled gas release. They might resemble natural comets under certain conditions. He suggested that 3I Atlas could hypothetically be such a probe, or a fragment of debris from a destroyed spacecraft or defunct light sail. To support this notion, Loeb cited the object's relatively tight dispersion of trajectory solutions compared to typical comets at similar heliocentric distances, suggesting that its motion exhibited less perturbation from solar heating than expected. Nonetheless, JPL's orbital models attribute this steadiness to the object's size, estimated near 1.5 kilometers in diameter, and its slow rotation rate of roughly 14 hours, both factors that naturally reduce jet-induced variability. Loeb also drew attention to the uncertainty in mass estimates and density modeling. Because 3I Atlas's nucleus has not been directly resolved, its mass must be inferred from its brightness and assumed albedo. Depending on the true reflectivity, calculated densities vary between 0.3 and 1.5 grams per cubic centimeter. Loeb argued that if future data confirm a higher albedo and lower mass, the object could be less dense than typical cometary nuclei, perhaps resembling a hollow structure. As in his earlier work on Oumuamua, Loeb framed his approach not as an assertion of alien origin, but as a methodological stance that outliers should be treated as opportunities for hypothesis testing rather than prematurely dismissed as natural. He proposed that if even one interstellar object were proven artificial, it would mark the most profound discovery in modern science. To investigate this, he encouraged targeted radar and spectroscopic campaigns for 3I Atlas, arguing that reflected radar signals could constrain surface conductivity and composition more precisely than optical observations. He also called for time-resolved spectroscopy to identify anomalous emission lines, which might indicate exotic materials or chemical signatures inconsistent with typical cometary ices. The broader scientific community responded to Loeb's speculations with cautious skepticism. By October 2025, a broad scientific consensus had emerged around 3I Atlas that it behaves entirely like a natural interstellar comet. Teams from NASA, ESA, and several leading universities confirmed that its hyperbolic trajectory, minor non-gravitational acceleration, and bright coma are all consistent with known cometary physics. Planetary scientist Karen Meach of the University of Hawaii emphasized that 3I Atlas's activity matched what would be expected from a volatile-rich body heated for the first time, while NASA's Paul Chodas at CNEOS reaffirmed that its orbit fits a standard gravitational model, with only slight adjustments from sublimation. The European Space Agency's NEO Coordination Center analyzed more than 800 global observations and found no signs of controlled propulsion or unnatural motion. Its report noted typical brightness variations, consistent with a slowly rotating nucleus. A peer-reviewed paper in Astronomy and Astrophysics concluded that the data strongly support a natural origin. NASA's October 15th statement agreed, confirming that 3I Atlas's composition, dominated by water vapor and carbon monoxide, mirrors that of other dynamically new comets. Observations from JWST's NIR spec instrument detected normal 2.7 micron water and 4.3 micron carbon dioxide bands, and no trace of artificial materials or anomalous spectral lines. Avi Loeb of Harvard, however, continues to raise open questions, suggesting that isotopic analysis of elements such as hydrogen and nitrogen might someday reveal the comet's stellar birthplace. He has also noted its high carbon monoxide content, though planetary chemists point out that carbon monoxide-rich comets are not uncommon. Loeb's Galileo project compiles open data from multiple observatories, promoting transparent investigation of interstellar visitors. Yet, all available evidence points toward 3I Atlas being a natural traveler from another star system. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.